system to send single-stage into low Earth orbit. Yeah, it's awesome. I can't wait to hear more about what they've been up to. And her talk is titled, Beam the Power Up, Scotty. Please join me in welcoming Laetitia.
Thanks for your great introduction, and thanks for the fun reference to Star Trek. We're going to talk today about boldly going where no one has gone before. For those of you who don't know about Escape Dynamics, we are developing an externally powered system where energy needed for the space vehicle to reach orbit is not stored on board the vehicle, as is the case with chemical rockets, but where that energy is wirelessly transmitted to the vehicle using a microwave beam. So using microwave-powered propulsion is really what we think is the next giant leap in space access. And so I'm very excited to be with you today to talk about that. And I will structure my keynote today around 3 key areas. First, I will talk about why and how we can and must move beyond chemical rocket. Then I will discuss the externally powered space launch system that we are deploying. And finally, I will wrap up with where we are and a company announcement that I'll be making today and for which we have a press release out this morning, which I think will go to show you that indeed boldly going where no one has gone before. So to start off, I think when we think about space access and orbital launch, there is one image that we all think about, and it's been that same image for now over 50 years. That image is the image of a chemical rocket where 90% of the mass fraction of the vehicle is for onboard fuel. Now, chemical rockets have served us really well over the past 50 years. There has been 2 major challenges that have been left unaddressed by the industry. The first is the cost, which has remained prohibitive for most, but the most valuable payloads. And the second is the lack of routine on-demand launch opportunities. Another thing to note about chemical rockets is that there is a fundamental limited efficiency that is directly rooted in the rocket equation and which dictates that close to 90% of the mass fraction of that vehicle needs to be allocated to the fuel. And so that means only 10% is left for payload and for structure, which makes reusability extremely challenging. Another thing that is rooted deeply in the rocket equation is that chemical rocket will never reach specific impulse above 400 seconds, and we know this is below the threshold required for a single stage to orbit spaceflight. So why do I bring this? Because we think that the future is really in reusable single-stage to orbit space planes. And the reason microwave-powered launch is the next giant leap in space flight is because it has the capability to produce specific impulse that is above the threshold needed for single-stage to orbit operation. With reusable single-stage to orbit operation comes aircraft-like operation to space, the ability for smaller payload to fly as a primary payload, and finally, 100-fold decrease in the cost of access to space for payload up to 200 kilogram compared to what they would have paid on a chemical launcher today. And I'm saying 200 kilogram. There's something magic about that number because this is where we minimize the cost of the ground infrastructure, but obviously we can scale those payloads over time to 1,000 kilogram and more. Now, let me tell you why now is the time for microwave-powered propulsion. Externally powered propulsion is not a new idea. In fact, it was first theorized in the 1920s by none other than Tsiolkovsky, who brought to us the rocket equation and wrote in the spaceship in 1924 that the most efficient way to go to space will not be using chemical rockets, but will be using millimeter wave energy that is beamed to the vehicle. Now, of course, a lot of technology breakthrough had to occur before this could become a reality. And amongst those breakthroughs, the development of phased array technology in the radio telescope industry, which we're actually using in reverse, the development of the gyrotron technology throughout the 70s and 80s, and in some way, and more importantly, for the purpose of the timing, some other advancement that occurred as recently as this very decade. And this advancement include industrial scale energy storage battery system, advances in the particle accelerator industry around fast discharge of energy, and advances in materials around ceramic matrix composite that, as you will see, is a key part of our vehicle, of the heat exchanger of our vehicle. I'd like to also make a note to Caltech and NASA Ames that have done wonderful investigative work in that field because technological breakthrough and advances don't happen with a lot of smart brains that are working on the same topic, and so they should be recognized for that. But now the fun part, let me walk you through what our launch system looks like. I will break down for you the ground infrastructure element, and then we'll talk about the reusable space planes. So on the left here, our team has designed and patented a system which is based on an energy storage system coupled with a mechanism to discharge high voltage DC energy into a bank of high power microwave sources. The total energy required to launch a 200 kilogram payload to orbit is 800 megawatt over a 300 second duration, which is a duration that the spacecraft takes to reach orbit. And that's equivalent to an industrial scale battery system of about 65 megawatt hour, which you can fill over up to a 24-hour period, in which case the draw that you represent on the grid is a mere 3 megawatt. So that problem is solved. The second piece of the ground infrastructure is here the high power microwave sources, also known as gyrotron. Those gyrotron are today used mostly in plasma fusion and high energy physics experiments. There are only a couple of them that are produced a year globally, and thus at quite expensive rates. And so one of the key areas in which our team has worked is advancing this technology further and redesigning the gyrotron so we can build more affordable gyrotron. We will need about 800 of those gyrotron for each of the 2 arrays that we will have for a space launch system. So this is a key element for us to advance. The third and last piece of the ground infrastructure is the phased array of antennas. So as you can tell, we're using a modular approach to beaming that energy to the spacecraft. And what that modular approach gives us is both a lot of redundancy in the system and the ability to control the width of the aperture that we have on the ground, so we can focus the energy at various ranges. Our team also designed, patented a side lobe suppressing system so that we could capture the nominal side lobe that you generate when you beam energy, which was also one of the major challenges that had not been solved before. And finally, moving on to the space plane and the microwave absorbing heat exchanger. And for that, I will move over to a closer up view of the vehicle. And I think that the first thing I want to point out about the vehicle that hopefully strikes all of you is that it is pretty simple. It's essentially a tank, a turbo pump, a heat exchanger, and an aerospike nozzle. I mean, of course, your payload bay, but it's overall very simple compared to a chemical rocket. Those vehicles can be built for less than $10 million and will carry payloads of 200 kilograms to orbit. The way thrust is generated is that microwave energy is beamed onto the heat exchanger. Meanwhile, we're releasing hydrogen from the tank through the turbo pump where it's being pressurized, and it then flows through the heat exchanger and is exhausted at the back of the vehicle, generating the thrust required for the vehicle to reach orbit. With the externally powered propulsion vehicle, the beauty is that you reach propellant mass fraction as low as about 70%, which means you have a full 30% to allocate to payload and structure. This is plenty. In a world where chemical rockets only have 10%, that means your payload efficiency can increase to 10%, and that means a lot more to allocate to your structure, thus allowing for reusability. And throughout the trajectory that we have planned for the vehicle, we paid close attention that the mass would be 7 so that we could, of course, take satellite payloads on board. Now let's take a closer look at the arrays. We have 2 arrays, the takeoff array that you see here, and the booster array, which is over here. Both arrays are about 400 megawatt of high power microwave energy. They're separated by about 200 kilometers so that the booster array takes over when the vehicle is out of the range of the takeoff array. And that's about it on the array. What I'm going to show you now is an animation of our launch sequence, which hopefully will give you a great sense of what our launch will look like. So the vehicle is here on the space launch, vertical takeoff position. It was just fueled in hydrogen a little before takeoff. That slopey building here houses 800 high-power microwave sources and antennas that are directly beaming to the heat exchanger on the belly of the vehicle. Hydrogen is being flown through and exhausted at the back, and this is all of the energy that is provided for the vehicle to take off. As the vehicle accelerates, once it reaches the handoff point, the booster array takes over. What you're seeing here are the side lobe suppressing system, which are water-jacketed radome around the antennas. The vehicle reaches orbit. It's in orbit and release the payload and open the payload bay door on the apogee, which you'll see momentarily. Once the satellite releases its payload, it uses cold gas thrusters to slow down and start its re-entry. As the vehicle re-enters in the atmosphere, The ceramic matrix heat exchanger also serves as the main thermal protection system for the vehicle. The vehicle lands and is ready for a quick inspection, reloading, refueling, and ready to go again. So now I want to show you where we are on the path to making this actually happen. We are 3 years into an 8 years plan. We spent the first 3 years in designing, patenting all key aspects of the system. We also prototyped high power microwave generation and wireless energy transfer systems. And now that we have those systems in our lab, we started engine demonstration and wireless energy transfer demonstration. Following this, we will start a phase of flight and drop test. And around right before the end of the decade, we will start building the infrastructure, and at the turn of the decade, send our first payload to orbit. This is some of the hardware that we have built and is in use in our lab today. On the left here is a 100 kilowatt gyrotron, again also known as high power microwave source, that transforms the grid energy into high power microwave energy. It functions at 92.3 gigahertz in continuous mode, and the system that we will use for the space launch system are 500 kilowatts. So they're a scaled version of what you're seeing here on screen. This is our first antenna. The antenna that we will use for the launch system will be 8 to 10 meters antenna. Again, a scaled version of the antenna that you're seeing on screen. We also have a big effort ongoing in the fields of material, in particular around ceramic matrix. The first materials that we have tested are actually silicon carbide, but we are continuing our effort to be able to manufacture silicon carbide ceramic matrix composite, because our team established that ceramic matrix composite would be the best materials for the heat exchanger as far as all the flight properties that they had, combined with the microwave absorption properties that we can give those materials. We have been pursuing a number of tests in the lab with all those new systems that we have. We have been pursuing both low power beaming tests and high power beaming tests. The low power beaming tests have essentially been tests for tracking of a UAV inside the lab using a 50 milliwatt power source, whose beam is actually similar in shape to the one of our gyrotron, so that later on we could just substitute the gyrotron for that beam, and which we plan when we take this experiment outside our lab. And the other experiments that we have been pursuing are to beam with our gyrotron onto a heat exchanger and measure the the specific impulse using a heat exchanger and flowing through helium through that heat exchanger. We were able to show in this experiment also the ability to completely shut down the beam within 200 nanosecond of an interlock trigger event, which is also something that we pay close attention to as we do this experiment to prove all the safety procedures. Let me show you some of the videos of our recent demonstrations. So this is a cut of the design of our gyrotron. And this is our lab in Broomfield in Colorado with some of our team members working on the gyrotron. You saw a very short cut of a 16 feet long enclosure that we have and that we're using to do this experiment. And here you're seeing a 3D animation so we can show you how we're beaming onto the heat exchanger, which is a complete system of a microwave-powered thruster, really. Now moving on to the tracking demonstration using low power. So the power here is not used to power the UAV again. This is just for tracking purposes. We have put LEDs on the bottom of that UAV you see here. And when tracking works, you will see the LED actually flash up. And the speed at which we're tracking that UAV are in fact much higher than what will be required for our space launch system. So the one thing I'm most excited though to announce today, and which hopefully will show you that we are indeed boldly going where no one has gone before, is that we had successful tests with this full system of a microwave-powered thruster that demonstrated over 500 seconds of specific impulse, which is above the specific impulse of chemical rockets. And in hydrogen equivalent term, had we used hydrogen in the experiment instead of helium, would have been far beyond the level needed for single stage to orbit operation, which is 600 seconds. So I'm extremely excited about those results. I have a little cut here of the actual data of those results. As it came through when we were running the tests. So that's a run from June 11th, and as you can tell, the ISP was over 500 seconds, and we were beaming onto the heat exchanger for a total of a little over 12 seconds. But there are many other things to look forward to. Thank you. I think the whole team in Colorado is very excited by this and will be very thankful for your endorsement. It will mean a lot to them. I'm sure some of them are watching right now. And so we have another set of future exciting demonstration in the next couple of years. And so I wanted to just give you a flavor what to look forward to. The very first one is that we're going to take this experiment we just did in our lab outside the lab. Instead of using helium as a propellant flow, we're going to use hydrogen, which will give us much higher ISP. We think we will reach close to 750 seconds of ISP. We will also, and very importantly, instead of using a silicon carbide heat exchanger, this time use a ceramic matrix composite heat exchanger. And this is part of the ongoing effort that is happening at our lab and that we will pursue over the next couple of months. Following this next demonstration, you can look forward to the first demonstration of a continuous UAV flight powered with microwave energy. And following this, we will build the orbital vehicle and start demonstrating the first flight of the vehicle with a ground power array of about 20 megawatt. And then it's only about scaling the system so that we can reach orbit with a much bigger ground array. So that's it. The future is now. Please join us in helping us revolutionize space access. And I will be on a panel after this keynote, but I will be outside the room for any Q&A. Or we may have time for 2 questions, actually, I'm hearing from Curtis. So I will happily take 2 questions. Yes?
In the technology slide, one of your items was Marx modulator.
Yes.
What is that?
So the Marx modulator is a recent innovation in the particle accelerator industry, on for the system that allows us to discharge high voltage DC power into the bank of high power microwaves And this is a technology, an innovation that came up with a method to basically discharge at very high discharge rate. Other question? Yeah.
Do you think your beaming technology would be a good tool in terms of space-based solar power and bringing power back to Earth?
So there are a number of technologies that I think need to be evaluated in space, power beaming, and for beaming from space to Earth. There is a very interesting work out of Caltech, Harry Atwater's group in particular. We are for now focused on using the technology for orbital launch. We will explore other avenues to use the technology and other use cases, but for now, orbital launch is what we're focused on.
Yeah, I think the power beaming from above.
Yep.
And bringing it up that way as well.
Yeah, and so for power beaming from above, and if you're thinking power beaming from space to another planetary body, for example, there are other technology that may be better positioned for that, and this is why I was referring to the work that Caltech is doing in that field in the group of Harry Atwater as one of several other examples. So Rectena-based technology or other technology that are, I think, very interesting in that field.
Thank you.
You're welcome.
Can this technology be used for human space exploration? And in particular, I'm just radiation concerns due to the method of power transfer.
Absolutely. And this will be the last question that I will take, I was just told. But so the radiation concern have to do with the side lobe that are created when you beam microwave, and microwave that could could payload bay, or if we had a human in on the flight. So the way we're building the vehicle is to isolate all the key parts of the vehicle from microwave, and so we're able to do that. And this is absolutely a technology that we plan over time to get human rated, but we will start with payloads. Thank you very much.